Okay, good morning, students. We're going to continue on the Lewis Structure Labs, and we are going to be looking at hydrogen cyanide, so that HCN. So with step one, what we're going to do is we're going to look at the valence electrons on each of the atoms. Okay, and how we're going to do that is we're going to be looking at the periodic table, and I'm going to be looking at the trend, which is that if you look at the column, you can determine how many valence electrons are in each atom. So in our molecule, the ones that we have are going to be hydrogen, carbon, and nitrogen. So in hydrogen is in column 1. It is going to have 1 valence electron. Carbon is in column 4 if you do not account for the d orbital. And then nitrogen is going to be in column 5, so that's going to have the 5 valence electrons. Okay, so let's put them in over here. So that's 1, 4, 5. So in total, it should be 1 plus 4 plus 5. Together, it's going to be 10. Okay. And in step 2 of this procedure, we're going to be deciding which of these is going to be in the center. And so how we're going to do that is we're going to be looking at our periodic trend of electronegativity. So electronegativity is going to increase going to the right of the periodic table and also increase going up the periodic table. The way I like to think of it is fluorine is the most electronegative atom. So if you get closer to fluorine, you're going to be more electronegative. So comparing nitrogen and carbon, nitrogen is going to be the more electronegative atom. So carbon is more likely to be the central atom. And then with hydrogen, hydrogen can only make one bond. So it's typically not going to be in the center. So we're going to leave carbon as the central atom. In step 3, what we're going to do is we're going to make a skeletal structure, thus connecting all the atoms together. So making bonds between hydrogen and carbon and nitrogen and carbon. I really like to keep track of how many electrons I have. So I start out with 10 total. So I'm going to put that here. And I'm going to put how many I used. So I used 2 here and 2 here. So in total, I've used 4 so far. So I have 6 electrons left. Okay, now in step 4, I'm going to put that 6 over here just so I remember that. In step 4, what we're going to do is we are now going to put lone pairs in, but we're only going to put them, or we're going to start by putting them on the exterior atoms. So I'm going to put them on this nitrogen. Now, we remember that hydrogen only needs 2 to fill its duet, and that'll make it a stable atom. And then nitrogen, we need to fill its octet, so that's why we put 6 around it. And over here, we're going to keep track of this, so we just put 6, so we have 0 electrons left. But now what we're going to do is we're going to look at the carbon in the center, and we're going to see that it has 2 bonds, or 2 electrons in this bond and 2 electrons in this bond. So it only has 4 electrons in total so far, which means that it doesn't have a full octet. So because of that, we're going to go to step 5 in the procedure. And in step 5, what we're going to do is we're going to see if we need to make any extra bonds to make it more stable. And basically what we're going to do is we're going to take these 2 electrons and move them down to make a bond between carbon and nitrogen. So let me redraw that. Okay. So it's going to look like this. And now nitrogen is going to have 2 sets of lone pairs instead of the 3. And we're going to recheck, and we're going to see if carbon now has a full octet. So it has 2, 4, 6. So it does not have full octet. But let's double check nitrogen just to make sure we didn't miss anything there. So we have 2, 4, 6, 8 electrons around it, so that one's still good. Now, what we're going to do is we're going to want to take another pair and put it down here to make a triple bond between carbon and nitrogen. So 1, 2, 3 bonds, nitrogen and a hydrogen over here. And now we're going to double check and see if our octets are full. So for carbon, we have 2, 4, 6, 8. Okay, because it has 4 bonds around it. So it has that full octet. And now for nitrogen, oops, we actually forgot to draw in the lone pair. For nitrogen, we have 2, 4, 6, 8 electrons, so that octet is complete. So this is going to be our final Lewis structure. Okay, so now that we have our Lewis structure, we can now determine the electronic geometry and the molecular geometry. So I'm going to use the table from the procedure, and to be able to do this, first we need to look at the number of electron sets. So looking at carbon as a central atom, we want to see how many electron groups are around it. So we see 1 here and the second one here. Now we would think that each of these bonds makes 1. However, we're looking at electron groups. So between carbon and nitrogen, there is only 1 set of bonds, that triple bond counts as 1 set of electrons. And then the hydrogen carbon bond also counts as 1. So we are going to be looking at this group. So due to that, we know that our electronic geometry is going to be linear. And now for molecular geometry, we're going to be looking for lone pairs around our central atom. So over here, we look at carbon, and we can tell that there are 0 lone pairs. And this line's in the wrong spot. Sorry about that, you guys. But over here, oh, that's not right. Sorry, we're going to be looking at this one. So there's no lone pair, so the molecular geometry is also going to be linear. Okay. Now, the next thing we want to do is we want to look at the 3D form of it. And so how I'm going to do that is I'm actually going to be looking at a website called MoldView. And so this one's really nice because you can see the molecule in 3D and you can move it around, see what it looks like in a 3D form rather than a 2D. So what I'm going to do is I'm going to draw in our molecule. So ours is made of CHN. Okay, and I'm going to make a bond between the carbon and the hydrogen. And I'm going to make a triple bond between the carbon and the nitrogen. And I'm going to make that into a 3D form. And as you can see here, it is linear, just like we drew it on our paper. And no matter how we rotate it, it always looks linear. It's just one single line. Okay. And that's going to be it for our hydrogen cyanide.